Hello AP Physics and welcome back to another video. So far this year, we've talked about translational motion. And so all these big ideas that we've gone over, kinematics, forces, energy, momentum, we were considering basically a point mass and just examining how these different forces cause an object to move through space. So we're just seeing it shift left, right, up, down. What we're getting into in this new unit is rotational motion. And so rotational motion, we now have this fixed shape with a defined axis of rotation, and we can see this object actually rotate, change its orientation, and rotate around the axis of rotation. We're going to go through all the same big ideas with rotational motion as we did with translational motion. And we're going to start off today by looking at rotational kinematics and defining these rotational variables. So a quick recap of what we've done with translational or linear motion. We started off the year, we defined an object's position. We represent the position with the variable x, and we know our SI unit for position is meters. If we're thinking in one dimension, then we just have a coordinate point somewhere on our number line, and maybe we could even say x naught is the initial position of the object. Let's take a look at what we're measuring for rotational motion. So I mentioned that we have this object with a fixed shape, and we're going to be able to see how it's rotating through space. So what we're measuring, the angular position, is going to be a measurement of theta. So what angle is the object at relative to a reference line? Now from geometry, we have this arc length idea, and we can use this theta equals S over R. We'll really get into this if we're trying to convert between translational variables and rotational variables. But S is our arc length, and R is the radius of the circle. And so if we go ahead and write that onto our figure here, so R is the radius, and S is the arc length, so the distance kind of along the circumference that the object perhaps has traveled. And so angular position, again, we have theta, and our SI unit for angles will be radians. So if we have the angular position, we're going to measure that position in radians. And we can go ahead and set that equal to S over R here as well. All right. Next, we define displacement. And displacement was the change in position, the object's final minus initial position. For linear motion, still measured in meters, delta x was equal to final minus initial, or x minus x naught. If you prefer x final, xf minus xi, x initial, you're welcome to do that. If we use our number line down here, we have 2 points now that we measure the displacement between, and the displacement always points from the initial position to the final position. Displacement is a vector. So it points toward the final position, and it is the separation distance between x and x naught. For our rotational motion, we're going to have a similar idea. We have angular displacement, so the change in the angle between, two positions. If we say this initial angle over here. We can call this theta naught. And then between where it started to where it ended, this large angle we're going to call theta. So then the change in the angle is this measurement here. So delta theta is, again, the final minus the initial angle when measured from a reference. So delta theta is theta minus theta naught. All right, still measured in radians. All right, from here, we built some of these kinematic ideas by relating how things changed with time. So the next thing we looked at was velocity, and velocity described how our displacement changed over time. It's measured in meters per second, and our variable for linear velocity was v. So v was delta x over t, how that velocity changes over time. Right, angular velocity is going to be built off the same idea. Our variable for angular velocity is the Greek letter omega, so it kind of looks like a curly W, and it's defined the same way. It's angular displacement over time, so delta theta over t. And if we think of delta theta was radians, so divided by time, radians per second is our SI unit for angular velocity. All right, our last definition for this intro to kinematics, we have acceleration, which is the change in velocity over time. So velocity meters per second was meters per second squared is our SI unit for acceleration. And we call acceleration A was delta V over T. We can also measure how an object's rotation is changing over time. Is it speeding up? Is it slowing down? So it's going to be the change in omega over T. Our variable we'll use for angular acceleration is a Greek letter alpha. So alpha is delta omega over t, and likewise with the units, radians per second squared. All right, so there's a one-to-one. We have the same kinematic relationships as we had for linear motion. We have a lot of Greek letters showing up, so you'll want to get familiar with these as quickly as possible, because that's going to make the whole rest of this unit go much more smoothly. The faster you kind of associate theta with position, omega with velocity, and alpha with acceleration, it's going to go much more smoothly. All right, we'll end this video here, and we'll take a look at some examples next.